Hello, today we're going to talk about reactivity 3.4.6 and 3.4.7. These are higher level only topics, and it's all about Lewis acid and base reactions. So we've already talked about Arrhenius acids and bases and Bronsted-Lowry acids and bases in the past. Another definition of acids and bases are Lewis acids and bases. And Lewis kind of flipped the script, and instead of talking about acids and base reactions in terms of like hydrogen ions or hydroxide ions, he talked about it in terms of lone pairs of electrons. So the definition here of a Lewis acid, like this, Lewis acid, is that a Lewis acid is a lone pair acceptor, an electron acceptor. A Lewis base, on the other hand, is a lone pair donor. So that means that this is very closely related to what we've been talking about in this section, which are electrophiles and nucleophiles. An electrophile can accept a lone pair of electrons, so that makes it a Lewis acid. A nucleophile donates a lone pair of electrons, which makes it a Lewis base. So really, this is just another way of describing these reactions, is by looking at where those pairs of electrons are moving or being shared for particular reactions. So let's look at an example of this. Let's use a very typical acid-base reaction so you can see what's going on. Let's say I have a hydrogen ion. Write it a little clearer. Hydrogen ion. And then I have ammonia. Ammonia is a weak base, like this. So when these two react, the hydrogen ion is coming from our acid, or is acting as the acid. The ammonia is our base. And what's happening when a new bond is forming, you're going to form ammonium, like this, the ammonium ion, which has a positive charge. So you're forming a new bond there. And what's going on is that the nitrogen is donating the two electrons in its lone pair to form a coordinate covalent bond with the hydrogen. And so because of this, since hydrogen is accepting that lone pair, it is a Lewis acid, and the ammonia is donating a lone pair, it is the base. That also means that your hydrogen is your electrophile, because it is attracted to the electrons from the nitrogen, and the ammonia is the nucleophile in this case. This is also a good example of a Bronsted-Lowry acid-base reaction, because the base is the ammonia. It accepts the proton, which is the hydrogen ion. So just because it is a Lewis acid-base reaction doesn't mean it can't also be a Bronsted-Lowry acid-base reaction. It's just a different way of talking about it. Let's look at another example, but let's use a boron compound. Boron is kind of weird in that it can have less than a full octet because it only has 3 valence electrons. So it can form compounds like this. This is boron trifluoride. But because of that, it only has 6 electrons around the central atom, so it is electron deficient, which means that it can act as an acid and it can accept electron pairs, a Lewis acid. If I were to react that with ammonia, which we talked about on the last one, which has that lone pair, which has that extra pair of electrons, it can act as a Lewis base and donate those electrons to form a coordinate bond with the boron there. So you'll wind up with this compound. Like this, and everything has a full octet, and this new bond that's formed, that's the coordinate covalent bond. Okay, so this is our example for this one. The BF3 reacts with the fluoride ion to form BF4-. Use Lewis diagrams to explain how this reaction is a Lewis acid-base reaction, and state the type of bond. So there's BF3, and the fluoride ion looks like this. And I'm going to go ahead and draw all of the lone pairs on this one. I didn't on the previous slide for simplicity, but those are all of the lone pairs present. So the boron is electron deficient. It has less than a full octet, so it can accept an electron pair from the fluoride ion, like this. So this is acting as our Lewis acid, and the fluoride ion is acting as our Lewis base. And you are forming this boron tetrafluoride ion. And the new bond that formed is a coordinate covalent bond. So it says, why is that reaction that we just looked at between boron trifluoride and the fluoride ions, why is that not a Bronsted-Lowry acid-base reaction? Well, Bronsted-Lowry acid-base reactions have to have a proton being transferred. And so there's no hydrogen involved in that reaction, no proton being transferred, so that's why it is not considered a Bronsted-Lowry acid-base reaction. It is a Lewis acid-base reaction. Okay, so this section links to reactivity 3.1, which is all about acids and bases. So what is the relationship between Bronsted-Lowry acid bases and Lewis acid bases? So Bronsted-Lowry acids donate hydrogen ions or protons. Lewis acids accept electron pairs. And so hydrogen ions can accept electron pairs. Bronsted-Lowry bases will accept protons. So they have to have some way to accept that positively charged proton and take that in or take that from the solution. Whereas Lewis bases will donate electron pairs. So Lewis acids and bases, it's the more broad definition. So like anything that can donate electrons can typically form a reaction by donating those electrons to the hydrogen ion and take it in. So Lewis is the broader definition. Bronsted-Lowry focuses on the protons. So for this also links to structure 2.2, coordination bonds. Do they have any different properties from other covalent bonds? They will typically, the biggest thing you need to know about coordination bonds is that both electrons are coming from one of the atoms, one of the two atoms in the bond. Whereas a typical covalent bond is going to have one electron coming from each of the atoms, and when they share, it forms that covalent bond. Coordinate bonds is just both electrons are coming from one of the atoms. So that is the difference that you should recognize and understand.